Hello everyone, welcome back to my channel Deep Understanding of Research Papers. Today I will explain a new paper called BERTphone, Phonetically-aware Encoder Representation for Utterance-level Speaker and Language Recognition. This paper was recently accepted in Speaker Odyssey 2020 and it is available in ISCA website. The authors are Shaoshi Ling, Julian Salazar, Yuzong Liu and Katrin Kirchhoff. And this paper is coming from Amazon's AWS AI group, and the tutorial is going to cover the introduction of the paper. Then we will explain what is this BERTphone pre-training scheme. Then there is something called TaskSpecific Model, which basically the idea of the paper basically takes taking the BERTphone embeddings and then using them for the speaker and language recognition tasks. Then we will explain the experiments and finally we'll see some results. So as many people may be knowing, transformers are like the state-of-the-art models in a lot of NLP and speech related problems. And if you see today's state-of-the-art machine translation systems, for example, or any take any NLP related tasks, many of them started using transformer models recently, and they obtain state-of-the-art results for many of NLP tasks like emotion recognition or sentiment analysis and machine translation and so on. And after this breakthrough of NLP related tasks using transformer, many people also started using transformer models for speech applications, and recently many people have published how to use transformers for speech recognition and many other tasks. And recently I submitted few papers into interspeech on using this transformer for language recognition as well. So the idea of transformer is basically, if you go and read about this transformer, the original 2017 paper, the paper name is Attention is All You Need, and the tutorial is also available in my channel. So the idea is to use something called attention blocks, so something called self-attention or multi-head self-attention blocks, to learn the contextual representation through contextual representation of the text data. Like initially it was published for text, and people have shown it can work for speech also. So the idea is to build the contextual representation starting from just the words, like word embeddings, to higher level representations, like the system should be able to understand the semantic and syntactic relationship of the words within a sentence. So, and it is very successful in NLP, and the same idea is also used here. So basically the idea is to learn a phonetically aware contextual representation from audio directly, and those representations are much helpful for language recognition and speaker recognition tasks, right? So and we will see like how this is done in the coming slides. And basically the transformer is not directly used as the classifier. So basically what they do is they take the transformer model and they learn these contextual representations from the audio, and that is going to be used as a pre-training base model. And the pre-training base model features are extracted during classification. Basically, let's say you have a classification task like speaker recognition. So what they do is they train the transformer model using unsupervised technique. So basically it's not exactly unsupervised. Usually in case of NLP it is unsupervised, but in this case there is some supervision. I'll explain how it is. And once the pre-training is done, what you can do is you can simply extract the top level embeddings from the classification layer. Let's say, for example, if let's say this is your transformer, let's call it TR, and you have audio. So once you train this transformer using unsupervised technique, assume it is some sort of semi-supervised training, right? So once you train it, so you can feed any audio and get these high level embeddings, right? So these embeddings, let's call them as Z, and so the Z will represent some phonemes relationships, basically the contextual representation of the phonemes, right? So that's how you learn the transformer and then use those embeddings for the speaker recognition and language recognition tasks. And we will see how to do the pre-training. So the pre-training is done using two different losses. So one is called reconstruction loss and the other one is called CTC loss. So in the old, if you see the old the original transformer model, they don't use any of this CTC or anything. They just use the reconstruction loss. Sometimes people also use something called contrastive loss, so that is a different thing itself. So the assume reconstruction loss is something like given an input, you are reconstructing something which is related to the input itself. Like in case of audio, you are reconstructing the spectrogram itself, right? And that was the idea, but in this case it is a little bit different and it's very interesting. I'll explain how it is. And then, as I said, the pre-trained BERT model will be used as the feature extractor for language recognition and speaker recognition. And they show that they obtain state-of-the-art accuracy on LRE, which is the language recognition task, and also they obtain very good performance improvement for speaker identification task as well, right? And we will see the results in the later section. Now the BERTphone is basically the model name. So basically we will explain this BERTphone full architecture in two stages. One, we will explain the architecture model. So basically, like what are the components, like what is the input layer, what is the output layer, and so on. Then we will see this loss function, which is kind of very interesting, unlike the old BERT model, which just uses reconstruction. So this is the whole architecture. So basically, as I said, it has this transformer encoder. So transformer encoder basically consists of sequence of layers, sequence of self-attention layers. So think of these as self-attention layer 1, self-attention layer 2, and so on. Usually they call it as multi-head self-attention. So MHA 1, 2, 3, and you can have, let's say, n number of self-attention layers. And we will explain what are these self-attention layers. But the model is going to take audio frames, basically, let's say a sequence of MFCC frames. And the idea in case of in transformer is to take these input, which is in our case sequence of MFCC frames, and mask out some of the frames in the middle, right? Let's say I just mask out some frames in the middle, which is like this frame and this frame and this frame, right? So this masking means we just make it zeros, right? So just remove this, replace this column, which is a MFCC vector, by zeros, right? This is also a very well known technique which is called spec augment, which was published by Google back in, I think, few months ago. So the idea is just mask out, means just zero the vectors, right? And the same technique is used here. So spec augment, like just remove some of the frames, remove in the sense zero some of the frames. Like as you can see here, they are like marked here, and the idea is to reconstruct these masked frames here, right? That was the original idea of the BERT model or transformer model. So basically you take, BERT model. So basically you take the input and mask out some of the frames and try to reconstruct those masked frames. That way you are learning the contextual representation. So basically you are trying to understand what are these fill in the blanks words. For example, let's say in the case of the BERT original text model, if I tell you I am going to dash, right? So dash is basically the fill in the blanks, and that's how most of the time people also learn, right? Like kids, like when you go to when you are a kid, you are gone to school, and in school they give you these tasks, right? Like fill in the blanks, like guess the words, so these kind of things. And that is the intuition of the paper. So basically you are trying to understand the context by predicting the fill in the blanks, right? In this case, fill in the blanks are these frames, right? So that is the whole idea of the BERT model. But in this case, there is one more interesting thing happening. So instead, they are not only just reconstructing the frames, they are also trying to predict what is the phoneme sequence of this input, right? So phoneme sequence is basically, let's say if I say hello world is the input audio, and these are the phonemes for this, and you predict this phoneme sequence from this BERT embeddings also. So that way you are forcing these features, right? These features to have some phonetic content, right? If you don't do it, the model might simply learn to reconstruct the frame, which may not be just necessary to have some higher level representation in this embedding space. But if you add this loss, which is basically the predicting the phonemes using CTNC loss, you are also enforcing you are also enforcing these vectors, which are these high dimensional higher level BERT embeddings, to have some phonetic content, which will be useful for language identification as well as speaker identification. I think they'll be useful for speaker recognition also, not speech recognition also, but they have not done that experiment. But I believe this will have rich phonetic content, which will be much needed for any of the speech related tasks most of the time, right? So that is the whole idea. So basically they're not only just using the reconstruction loss just like BERT, but they are also adding this CTC loss by enforcing basically making the model to predict the original phonemes, so that the embeddings will have that information as well. So that way these vectors are much helpful, and that is the differential factor between the original BERT model and this and this BERTphone model, right? And so as I said, the transformer, so how do they do that? They have transformer encoder. So the transformer encoder is basically, as I said, is a sequence of multiple multi-head attention layers. So basically the multi-head attention goes like this. So basically I think many people will be knowing, because these transformers are like very famous ones. So basically what happens is they have something called query and key and value matrices. So this query, key and value matrices in this case are just the output from let's say the first layer, like every layer. So usually this query, key, value will make sense when you try to understand these things in case of a machine translation or some sequence to sequence mapping problem, because basically the query will be some output prediction which will try to try to attend to the key and value, which are basically the input representation. But in this case, assume all these are same. Now this query will get will go through something called a linear block. So there will be 3 linear blocks which are different. So the linear block is basically one simple fully connected layer, right? And output of this will go into something called self attention. So self attention basically uses something called scaled self attention, right? Or something called scaled dot product attention. Sorry about this, dot product attention. So what is this scaled dot product attention? So many people will be knowing about attention. So attention is basically 2014 paper. If you go back and see, it is something like having 2 vectors, or let's say you have a query which just goes to the input vectors and try to select some of the interesting or important features, and then uses them through the fully connected layer and then put softmax. But in this case they use something called dot product attention. So dot product attention is kind of came right after the original attention paper. Basically it said instead of doing all this fully connected and all this thing, you just use the dot product, which is just you take the query matrix, you just take the transpose of the key matrix and then apply a dot product, right? That's just a dot product. It's a very simple thing. So once you apply dot product, you take the softmax, which basically gives you the attention weights, right? And then you use these attention weights and to select the actual output from value, which is same as key, and then you get the attention output, right? As simple as that. Then that is simple self attention layer. Now there is something called multi-head. Multi-head is basically instead of using instead of using only one linear block, use multiple m of them, right? M different linear blocks. So basically using something called m different attention heads, right? So each attention head will give you some information about so basically each attention will select some part of the input, and if you have multiple of them, all of them will contribute and select from different parts of it, right? Different parts of the input, and that way you get a lot of information selected by multiple heads, right? So that is the whole idea of multi-head self-attention. So I hope you go and read this transformer architecture somewhere so that you get the full understanding if you don't know about it, or you can just go and watch my tutorial in my YouTube channel. It's called Attention is All You Need, the paper name, and the tutorial is available, and I have explained it in detail. And this is the whole idea of the BERTphone model, right? So BERTphone is basically the pre-training architecture. Now assume you have the audio data and you know the phoneme sequence of the audio, or each of the audio segment, each of the audio input, and then you do this, you train the model, this big model, for lots and lots of having lots and lots of data for many days. Then you get this pre-trained model, right? Now what I will do is, sorry, before going into the task specific model, we need to understand the loss function also. As I said, we are using two different types of loss functions in the previous slide. So one is reconstruction loss. So the reconstruction loss basically takes the input, which are basically the frames, MFCC frames, and then try to reconstruct the masked frames, right? But instead of just reconstructing the masked frame, they are just trying to reconstruct everything, which is the entire spectrogram, and that way you can calculate the loss function very easily. And basically this ZT is the representation which we learn, basically the hidden representation from the BERT model. As we saw, the model had two different heads, this way and this way, and this is the final output, the blue color thing we had. These ZTs will go through fully connected layer, feed forward network, and they generate this XT cap, basically the prediction, the reconstruction of the XT, original XT, and then you sum over all the T, and then you get this the reconstruction loss per item, per audio, and they can sum over all the audio and then get the total loss. That is one loss, this reconstruction loss. Then we have something called LCTC. So LCTC is basically the CTC loss, which is basically negative of sum of I equal to 1 to n. N is basically the number of audio files, P of yi given xi, right? And this is negative CTC loss. This is just the CTC loss, and this P is basically is this, right? Let's call it as Pi and xi, and let's call this I and I. So basically what it does is it just takes the dot product, takes the product of all the conditionals while predicting the phoneme. So ST is one phoneme at the timestamp T, and X is your input audio, and then you take product of all these class conditional probabilities, and these probabilities, these conditional probabilities are like independent of each other, because ST given X is independent of all other outputs. So like it is not dependent on XT minus 1 or XT plus 1, unlike HMMs or anything. So that way it's easy to calculate. And then you have something, you just sum over all the possible alignments of Y, because usually the Y will be smaller than X, so you need to make X and Y similar. So that way you apply, you just apply some transformation. It has its own thing, so you can just go and read CTC. But what I'm saying is you have to make Y and X same. So basically the lengths should be same. So you append some blank symbols and repeat the same symbols. So all these things, and then you get a new S, which is basically the input aligned, and then you can compute this very easily. And then once you get probability of Y given X, then you sum over all the inputs, all the data, and then you apply negative, you get the CTC loss. Now you have CTC loss and the the reconstruction loss. Then you just add them with some scaling constant lambda, and then you get the final loss, which is L here, right? Then you can use the same optimizer, and then this basically falls into something called multitask learning. And if you know about it, it's basically predicting two things at the same time and then using the two information. So basically doing multiple tasks at the same time, right? It's very simple. Now we will come to the task specific model. So basically the task specific model basically takes the high level representations which are learned from BERT, the pre-trained BERT model, and then uses them through some sort of classification model. So I'll explain this classification model later, but let's understand what is this blue color inputs are here. So basically let's say you have the pre-trained BERT model. So basically the BERTphone model, right? And you have the audio. So you feed the audio, right? Audio basically the spectrogram. Then it was like this before, and then we had this layer which is basically having blue color things in the previous slide. So this basically has something called Z, and these Z's are Z1, Z2 and so on, capital ZT. So basically this is the final or a something called bottleneck layer. So the bottleneck layer basically has bottleneck layer basically is the last layer of the BERT pre-trained model, and then you take these hidden activities and then use them as the input to this model. So basically the idea is this model would have learned some phonetic contextual representation. Basically it understands what are the it understands two things. One is it has some acoustic representation basically learned through reconstruction. Second thing is it has this phonetic information, so basically the contextual phonetic information, because you are also predicting the phonemes, not only just reconstruction. So that way these features are like very rich in acoustic and phonetic information, and they are like easily classifiable because they already are higher level representation. They are not like MFCCs. They already a higher level representation, and they capture a lot of this high level information, and they are easy to classify. So what they do is they take this Z, it's a sequence of vectors, and then feed them as input to something called 1D convolution. So basically 1D convolution, it's similar to time delay neural network, takes 1D convolution kernels and moves them across time, and then you get frame level. So this like you have multiple 1D CNNs, and then this captures the frame level statistics, and then you use something called attention pooling. So the attention pooling basically is to pool all these frame level features into a single utterance level vector. So the utterance level, how do you get that? So you use something called attention pooling, and attention pooling is similar to like what we explained in the previous slide, self attention. Basically you have the W matrix and you have the input X, and then you apply a very simple attention layer, and then you get the utterance level vector, right? So that vector will go through feed forward network, and that will have some sort of capture something called segment level features. Then you can simply use a linear softmax layer with cross entropy loss and predict what is the language, right? Or in case of speaker, you just predict what is the speaker. And you can also extract these embeddings to compute the PLDA scores, or you want to compute EER and so on, right? And this is the idea of this task specific model. So I hope you guys understood. So the idea is very simple. So you use BERTphone model to with pre-training to understand to make the model learn this phonetic contextual representation and some acoustic representation. Then you use those vectors and use those embedding vectors, and then feed them to a task specific model, which is basically another model which takes this high level representation instead of the audio MFCCs itself. This is kind of done in the past. Like many papers are written for this bottleneck feature based LID or speaker identification, and then doing this pre-training on some other data, and then using these high level features for some other class. This is kind of very well known thing. So the idea is, in this paper, the idea is to use BERT to learn very good representation. So this is like not a completely new idea, so a known idea, but with the different types of architectures and so on, right? So that's about the whole paper. Now we will understand some experiments, and we will see what are the configuration used for pre-training LAD and SID. So for BERT pre-training, they use 40-dimensional MFCC, which are mean normalized. Basically CMVN is applied, and those features are extracted for every 25 millisecond window, and with every 25 millisecond, with a window of 25 millisecond and a shift of 10 millisecond, and they stack each frame. So they stack 3 consecutive frames so that the GPU memory is saved, and then they use 12 self-attention layers. So as explaining in BERT, we have this multi-head self-attention layer MHA, and these are like 12 of them in this case. And the D embeddings is basically the position embedding they add to this thing, and then D fully forward is 4 times of that embedding, and number of heads in each layer is 12, right? And they use batch size of 80, and then they use warm up for the first 3000 batches, and then with the learning rate of that much, and then they train it for 30 epochs. They train two models. So one is called Fisher BERT, which is basically uses Fisher English data, and then because that is a telephonic conversation, it's a 8 kilohertz data, and they use Tedlium data, which is a YouTube TED Talks, which is 16 kilohertz. There are two different BERTphone models. So one is trained on Fisher English, and another is trained on Tedlium, because there are two different. They use two different data sets. So they take the BERTphone Fisher BERT model representation for the Fisher speaker identification task, or speaker recognition task, and there are 172 hours of data from 5,000 speakers, and these are like standard speaker identification data sets, and you can go and read about this online, but not so important. And the same thing they do this for they extract embeddings from the Tedlium BERT model for the Voxel speaker identification task. And for language identification, they use the Fisher BERT itself, because they use the LRE 7 data for language identification, and then then similarly all the training and everything, it's a same thing. I mean, you don't have to worry about it, because these are like standard things, like standard data sets people use, and this LRE has 14 different languages, so on, right? So let's see the results. In the results section, this is basically for the speaker identification, and in speaker identification there are two data sets. One is this Fisher, and another is Voxel. So for Voxel they use Tedlium dataset for feature extraction or pre-training, and they use those features for the Voxel classification, and you can see the ER and DCF and so on. As you can see, this model, the expector, so it's not exactly expector. Actually, expector uses TDNN, but these people uses one-dimensional 1D convolutions. But anyway, they're like almost same. So they get around 1.23 ER, and if you compare all the models, all the previous published model like iVector, XVector, with all these new papers, you can see this model gets the best ER and DCF, both on Voxel and on Fisher. And same thing, they have tested it on language identification task as well, and these are the results. As you can see, this paper gets the best results, except in case of longer sentences, the DNN phoneme posterior paper gets the best ER and C average, right? But in all other cases, on an average, all other cases, the BERTphone model along with 1D CNN with self-attention pooling gets the best accuracy. And also they have done some ablation studies, basically with the varying lambda, basically giving weightage to the CTC loss and the acoustic loss. As you can see, in case of language identification, if you make lambda equal to 0, basically that is like making this reconstruction loss 0, but keeping the CTC loss, actually gives you the best accuracy for language ID. But in case of lambda equal to 0.2, basically you need to have both. In case of speaker identification, you need both acoustic representation and phoneme representation. This kind of tells that for language ID you might not need so much acoustic representation. You need a lot of phonetic representation. But in case of speaker ID, you not only need you don't need much of phonetic representation, but you need a lot of acoustic representation. This kind of also intuitively sounds good, sounds correct, right? Like because a lot of these PRLM based technologies, like PRLM based language identifications papers, were actually better than just these old techniques. So that clearly tells like you need a good phonetic representation for any language identification task. But for speaker ID, acoustic representations are important. That is a good observation. Second thing is they also see like what are the like they have also tapped a lot of these seen the attention weightage for different layer, and it looks like this. And as you can see, the attention weight for the higher layers are like Good. Um, and that's all for this tutorial. Thank you so much for watching this tutorial. This tutorial was a little bit longer than the usual ones. Like usually it used to be 20 around 20 minutes, but this is around 30 minutes because these papers are big actually. So the ODC papers are like 8 pages compared to any other like interspeech or ICAS papers. I think that's why this tutorial took a little bit longer. And thank you so much for watching this tutorial. If you like this tutorial, please give a thumbs up, and if you are not subscribed to my channel, please subscribe for more of these kind of tutorials. Thank you.